Now we're going to analyze these branches that we have obtained for a one-dimensional Bravais lattice with a diatomic basis. So this was our result for omega square, and we're going to analyze the behavior in the middle of the first Brillouin zone. So that's the long wavelength limit. So as lambda goes to infinity, k goes to 0. K is 2 pi over lambda. So what I see here is that there is a cosine Ka. So what happens to cosine Ka? Well, the Taylor series expansion of cosine theta around theta equals 0 gives us cosine 0, a first derivative of cosine minus sine, theta minus 0. Second derivative gives us minus cosine theta squared over 2 factorial. So cosine 0 is 1 and sine 0 is 0, so we obtain 1 minus theta squared over 2. So that is 1 minus k square a square over 2. So we're going to substitute that for cosine Ka into our result. So we have the 2m1 m1 square plus m2 square plus 2m1 m2, 2m1 m2 times 1 minus k square a square over 2. So that's going to give us 2m1 m2 and minus 2's will cancel, m1 m2 k square a square. So here what I have done is I have multiplied 2m1 m2 with 1 minus k square a square over 2 to obtain this result. So this is what I did. Okay, so then I have the square root here. And I can notice here that there's m1 square plus m2 square plus 2m1 m2, that is parentheses m1 plus m2 square. So I can write this result as omega square equals c m1 plus m2 plus or minus c m1 plus m2 square minus k square a square m1 m2 parentheses square root divided by m1 m2. Okay, so we can look at the positive branch and we can look at the negative branch. So let's look at the negative root. So then I will have c m1 plus m2 minus c. Now if I take this into m1 plus m2 parentheses, you can see that m1 plus m2 squared to the power 1/2 will become m1 plus m2. So when I take it out, I get a 1 minus k square a square m1 m2 divided by m1 plus m2 square root. So this divided by m1 m2. So that's going to be my first solution. That's the negative root. So for the 1 minus k square a square m1 m2 divided by m1 plus m2 square root, I noticed that since k is going to 0, this is 1 minus x to the n, which is 1 minus nx for small x. And x here is k square a square m1 m2 over m1 plus m2 square. So the square root is basically give me 1 minus 1 over 2. So 1 minus 1 over 2 k square a square m1 m2 divided by m1 plus m2 square. So I substitute that for the square root term. So I obtain c m1 plus m2 minus c m1 plus m2. With that simplification, I obtain approximately 1 minus k square a square m1 m2 divided by 2 m1 plus m2 square divided by m1 m2. Okay, so in c m1 plus m2 parentheses, I will obtain here 1 minus 1 plus k square a square m1 m2 divided by 2 m1 plus m2 square, m1 plus m2 parentheses, so I have taken that out, divided by m1 m2, plus 1 and minus 1 will cancel, m1 m2's will cancel, and m1 plus m2 will get rid of one of the squares. Therefore, for omega 1, I obtain c a square divided by 2 m1 plus m2 to the power square to the power 1/2 square root multiplied by k. Because this was omega 1 square, I have taken the square root. And you can see that this is linear with k, and it's in the form omega is equal to v times k. So that this is like the speed of sound, which is square root bulk modulus divided by the density of the medium. So it acts like a sound wave behavior, and omega 1 must be positive, so I don't take the negative root. So it's in the form of a sound wave, so it is called an acoustical branch. So, and sk goes to 0, omega goes to 0 is telling me that it is an acoustical branch. Now if I take the positive root, so instead of omega 1 square here, cn1 plus m2 minus cn1 plus m2, I would have a plus. So for the positive root, I would have the plus sign. So that gives me, with the plus sign, cn1 plus m2 parentheses 1 plus 1 minus k square a square over 2n1 plus m2. So I operate the cn1 plus m2 into this parentheses. So let's see what I did here. So I have cn1 plus m2, then I have plus cn1 plus m2. So instead of the minus sign here, I have the plus 1 minus k square a square, and then I have m1 m2 divided by 2 m1 plus m2 square, and this divided by m1 m2. So that's what I had. So for this term, cn1 plus m2 parenthesis gives me 1 plus 1 minus k square a square n1 m2 divided by 2 n1 plus m2 square, and so this is going to give me 2c n1 plus m2 divided by n1 m2, and then I will have minus c n1 plus m2 will get rid of the square here, so this is what will happen, and I will have minus c k square a square, and 1 m2 at the bottom will get rid of this n1 m2, 2 n1 plus m2. Okay, so this is what I will get. Now you can notice that as k goes to 0, this becomes 2c 1 over m1 plus 1 over m2. So m1 divided by m1 m2 gives me 1 over m2, m2 divided by m1 m2 gives me 1 over m1. So this is in the form 2c over mu, where 1 over mu is 1 over m1 plus 1 over m2, and mu is called effective mass. So when I set k is equal to 0 here, omega square is not equal to 0. So it's not in the form of the sound wave, so it's not an acoustical branch, it's called an optical branch. So here the oscillation frequency, angular frequency omega, contains the effective mass of the atoms within the unit cell. We can conclude that an optical mode is motion with respect to the center of mass of each unit cell, leaving the center of mass fixed. So the optical branch is describing the motion of the atoms with respect to the center of mass. So in the diatomic case, we have an effective mass 1 over mu, which is 1 over m1 plus 1 over m2. Now, so this is what I did to get this result. And if I look at the other limit, the first brilliant zone boundary, k is equal to pi over a, what happens there? So I go back to my solution. I will look for what happens at k is equal to pi over a. So I have to work on cosine ka as k becomes pi over a. Now cosine ka expanded into a Taylor series near k is equal to pi over a. So first I set k is equal to pi over a. That gives me cosine pi, which is minus 1. Then I take the derivative with respect to k, minus a sine ka, k minus pi over a. If you set k is equal to pi over a here, sine pi gives us 0. So the second term is 0. So this is going to give me 0. And for the third term, I will have another derivative, minus a squared over 2 factorial cosine ka. K equals pi over a will give me cosine pi, which is minus 1. So it becomes plus a squared over 2, k minus pi over a squared. So the answer is minus 1 plus ka minus pi divided by a squared, but the a squares will cancel. So I will have ka minus pi squared divided by 2. So if I substitute this result here for omega square, first term I had was c m1 plus m2 divided by m1 m2. So that gives me c 1 over m1 plus 1 over m2 plus or minus c divided by m1 m2. So that is what I had here, c divided by m1 m2. Now in parentheses I put m1 square plus m2 square plus 2m1 m2 cosine ka becomes minus 1 plus ka minus pi over 2 squared square root. So I noticed that I will have now m1 square plus m2 square minus 2m1 m2. So m1 minus m2 parentheses squared, and then the 2m1 m2 multiplied with ka minus pi squared over 2 will give me m1 m2 ka minus pi parentheses squared square root. So this now I want to isolate the second term here, so I take this into m1 minus m2 squared parentheses. That comes out of the square root as m1 minus m2. So I have a 1 for the first term in the parentheses, and then I have m1 m2 ka minus pi squared over m1 minus m2 squared. So if you set k is equal to pi, x is small, so I use the same result. 1 plus x to the n becomes 1 plus nx for x small. So omega squared becomes then c 1 over m1 plus 1 over m2 plus or minus c over m1 m2. m1 minus m2 parentheses, the square root turns this into 1 plus m1 m2 ka minus pi squared divided by 2 m1 minus m2 squared. So this is in the first Brillouin zone boundary. So I'm going to work on this result in order to obtain acoustical branch and optical branch behavior. So for the acoustical branch, if I take the negative root, I have omega square equals c 1 over m1 plus 1 over m2 minus c m1 over m1 m2 gives me 1 over m2 minus m2 over m1 m2 gives me 1 over m1, and I distribute this into the parentheses, so it's the first term, and in the second term I will have m1 minus m2 squared, getting rid of the m1 minus m2. m1 m2s will cancel, so I will obtain minus c ka minus pi parentheses squared divided by 2 m1 minus m2. So if you put this into c parentheses, 1 over m1 plus 1 over m2 minus 1 over m2 plus 1 over m1, 1 over m2s will cancel, and the second term, if you set k is equal to pi over a, becomes 0. So therefore omega square is 2c over m1, or omega is square root 2c over m1. So acoustical branch gives me square root 2c over m1 at the first Brillouin zone boundary. For the optical branch, I take the positive root, so c times 1 over m1 plus 1 over m2. Inside the c parentheses I will have, instead of minus 1 over m2 plus 1 over m2, instead of plus 1 over m1 minus 1 over m1, and the second term will become a plus c ka minus pi squared over 2m1 minus m2. K equals pi over a makes the second term 0, 1 over m1's cancel, and omega squared becomes 2c over m2, or omega is square root 2c over m2. So the optical branch gives me k equals pi over a square root 2c over m2. Now if I plot this result, my acoustical branch becomes 0 at k equals 0. Optical branch is square root 2c over mu. At the first Brillouin zone boundary, acoustical branch becomes square root 2c over m1. Optical branch becomes square root 2c over m2. So we have the same value at the first Brillouin zone boundary. And we see that there is a forbidden zone here. So these frequencies are not allowed. So what does that mean? So I have plotted this assuming m1 is greater than m2. Wave-like solutions will not exist for angular frequencies between square root 2c over m1 and square root 2c over m2. It's a characteristic feature of polyatomic lattice, and we can see that here the diatomic lattice acts like a notch filter. So if we summarize, we have analyzed the solution for the one-dimensional lattice with a diatomic basis, we looked at the long wavelength limit and we found that if we take the negative root, we're getting an acoustical branch. Omega is V times K, that is the dispersion relation, and this gives us as k equals to 0, omega is equal to 0. And for the positive root, we obtain what is called an optical branch, which gives us omega is square root 2c over mu at this point. So omega is square root 2c over mu. That is our result. And because we have this effective mass here, the optical mode is basically a motion with respect to the center of mass of each unit cell, leaving the center of mass fixed. We're going to look at the displacements more carefully to understand what is going on. At the first brilliance zone boundary, when k approaches pi over a, the acoustical branch gives us omega equals square root 2c over m1. The optical branch gives us omega equals square root 2c over m2. When we plot this result, assuming m1 is greater than m2, we obtain a band of frequencies which are not transmitted. So wave-like solutions do not exist for these values, and therefore the crystal acts like a notch filter. Some frequencies are forbidden.